All right, hey everyone, welcome back to our series on linear algebra. Today we'll be talking about linear independence and span, two notions that are really important for our subject. Um, so we've just finished talking about solving systems of linear equations. That was like Gaussian elimination and Gauss-Jordan elimination, right? Reduced row echelon form of matrices and stuff like that. So this topic is more of a hard pivot from that. We're going to focus in on linear combinations of vectors today. That was something that we talked about in 2.1. We mentioned it in 2.1 and we gave definitions earlier in chapter 1. And so today we're just going to really hyper focus on those kinds of things. So we have a leading question, which is the vector 1, 2, 3 a linear combination of these other two vectors, 1, 0, 3, and negative 1, 1, negative 3? So to answer this question, we can actually create a system of equations, right? So what does it mean for 1, 2, 3 to be a linear combination of these two vectors? It means that, let me write it this way. There are constants c1 and c2 such that if you take c1 times 103 and you add c2 times negative 1, 1, negative 3, you should be able to get 1, 2, 3, this vector. Right? And if we can find these constants, then 1, 2, 3 is a linear combination. And if no constants exist, then 1, 2, 3 is not a linear combination of these other two vectors. But notice this is secretly a system of equations. Let me write it out for you. It's c1 minus c2 equals 1. 0 plus c2 equals 2. And 3c1 minus 3c2 equals 3. All I did was distribute the c1 and the c2 and then add row by row. This system it's a system of linear equations, right? We need to solve for these constants. We don't know what they are. We can do that with techniques from section 2.2. So, right, we convert this thing into an augmented matrix. So 1, minus 1, 1, 0, 1, 2, 3, minus 3, 3. Okay, I will, well, what we'll do, we'll row reduce this matrix real quick. So just so that you see one more worked out example of row reduction, notice we have a leading 1 already. So we have to clear out that column by adding negative 3 row 1 to row 3. Row 3 minus 3 row 1. And that will give 1 minus 1, 1, 0, 1, 2, 0, and then we, 0, 0, 0. Fantastic. If you add, notice row 3 is literally negative 3 times a row, is 3 times row 1. So if you add negative 3 row 1 to row 3, it'll just clear out that bottom row. It's kind of nice. And if we just add row 2 to row 1, this thing will be in reduced row echelon form. So row 1 plus row 2. Okay, and that will be 1, 0, 0, 0, 1, 0. Row 1 plus row 2 will give us a 3, 2, 0. Let me rewrite that. Okay, this is in reduced row echelon form. And notice if we convert it now in keeping with Gauss-Jordan elimination, we have to now convert this back to the corresponding linear system. But notice it just reads C1 equals 3 and C2 equals 2. Oh, let me make that a little bit more obvious. 1c1 equals 3 and 1c2 equals 2. So in other words, the solution is just sitting right here for us. And apparently, in the context of our original problem, this c1 should be a 3 and this c2 should be a 2. Let's just check that. 3 times 103 plus 2 times -1, 1, -3 is, well, 3 times 1 is 3, 2 times -1 is -2, 3 minus 2 is 1, 3 times 0 is 0, 2 times 1 is 2, 0 plus 2 is 2, of course, and 3 times 3 is 9, 2 times -3 is -6, 9 minus 6 is 3. And sure enough, 1, 2, 3 is a linear combination of these other two vectors. Now, there's no reason that we should have dropped an entire row, right? That seemed kind of lucky that everything worked out and we did that one row operation. And it's possible that this system would have been inconsistent. If that was true, we would have just said that 1, 2, 3 is not a linear, or whatever the vector that we're trying to find, is not a linear combination of the other two. Okay? And that pattern, that's a general pattern, which is that if we had used the vectors that we're trying to use, if we had written the vectors that we're trying to use to make a linear combination as columns in a matrix, and then written the vector that we're trying to write as a linear combination as the augmented column in an augmented matrix, then whatever that linear system is, if that system is consistent, then the vector that we're trying to write as a linear combination is actually a linear combination of those other vectors. Let me say that succinctly in a theorem, okay? It's theorem 2.4, and this is one of the only theorems that we're going to use that doesn't have a proof. It's a very straightforward, it's an observation, right? It says that the system A augmented with B is consistent if and only if B is a linear combination of the columns of A, right? That was exactly what we did just now. We were given some column vectors. We created an augmented system, which we then went and solved. And the fact that that system was consistent gave us a solution for the scalars that we can use to multiply the columns of A by in order to obtain the vector B. Okay. Let's just do two more examples so that you can see this in action. Let's write down the augmented matrix for this system. So this system is 1, minus 1, 1, 1, augmented with 1, 3. The system is consistent. You can do row reduction. It's reduced row echelon form. Well, it has a unique solution. We'll just say x equals 2, y equals 1. Skip a few steps. Okay, you should probably go back and verify that this is the unique solution for this system. But what it tells us is that apparently 2 times 1, 1 plus 1 times -1, 1 equals 1, 3. Okay, and sure enough, that works out. On the other hand, if I had this system, notice I have x minus y equals 1 and x minus y equals 3. Those are two parallel lines, so the system will be inconsistent. But we'll just write that down real quick. 1, 1, minus 1, minus 1, 1, 3. If you row reduce this matrix, you're going to get, just subtract row 1 from row 2. Actually, let me write that. We have notation for that. Row 2 minus row 1 just gives 1 minus 1, 1 on top, and on bottom, 0, 0, 2. Now hold on. This is telling us that 0x plus 0y equals 2. Sorry, this is, yeah. So in other words, we have the inconsistent statement that like 0 equals 2. This is false, which means that the system is inconsistent. And so, by theorem 2.4, 1, 3 is not a linear combination of 1, 1, the columns of this matrix, right? 1, 1, and minus 1, minus 1. That makes sense, right? Because minus 1 is literally a multiple of 1, 1. So what are you going to do? Add two multiples of the same vector, essentially, together to get something that's clearly not a multiple of either one. That'll never happen. And here's this theorem 2.4 combined with this augmented matrix is a much cleaner way of saying that. Great. So one thing that's really important to us is the collection of all linear combinations of a set of vectors, right? So it's one thing to ask whether any one vector is a linear combination of a bunch of other ones, but another topic entirely is we can ask the question, what is the set of all linear combinations of a specific set of vectors? In fact, that's such an important concept, we give it a name, and we call it the span of those vectors. So let me give you the precise definition. If S is the set of vectors v1 up through vk, vectors in Rn we'll say, then the set of all linear combinations of those vectors is called the span of those vectors, or we call it the span of S. Notation, we just write the word span and then parentheses. Sometimes you'll see someone use angle brackets for the span. We won't do that in our class, and I don't believe the textbook does it either. But you may see that in other textbooks, or if you continue on to higher and other classes in mathematics, you may encounter that notation as well. So don't be fooled. It just means span, linear span. Okay. By the way, if the span of a set of vectors is Rn, a set of vectors in Rn, if the span of that set of vectors is all of Rn, then we call that set of vectors a spanning set. Okay, so let's do an example, although this example already has an error. So the span of these two vectors is R2, not Rn. Okay, Rn, that's not going to work. Okay, so it's early in the morning. I need coffee. This is very important. So to do this is a very interesting strategy. We want to show that the vector AB can be written as a linear combination of these two vectors. 2, -1, and 1, 3. So the augmented AB for any A and B, right? If we want to make any vector in R2 as a linear combination of these two vectors, then we need to we can't say what these entries in this vector are. We have to let them be arbitrary. So this is the setup. So the linear system has augmented matrix 2, -1, 1, 3, augmented with AB, like that. And now we have to go and row reduce. So for example, we're going to have to take half of row 1. Okay. So this will be like 1/2 A over 2, and then -1, 3, B. Then we'll add row 1 to row 2. So row 2 plus row 1. So 1/2 A over 2, 0, 7/2, and B plus A over 2. While we're here, I'm going to also double row 2. So that we have just whole numbers, right? So 7/2 doubled will become 7. And B plus A over 2 doubled is going to be 2B plus A. Yeah. Okay, and so on. We know the process for Gauss-Jordan elimination, but what we're gonna do, we're gonna have to. Well, I say all this. We're gonna have to, divide the bottom row by 7, and then add -1/2 of the second row to the first row, and so on. And that's gonna be some operation on these A's and B's. Let me put for you the final row reduced echelon form for this matrix. So it looks like this: 1, 0, 0, 1, augmented with B minus 3A over 7 and 2B plus A over 7. So, in other words, the vector AB is okay. It's going to be B minus 3A over 7 times the first vector, because the first constant is this constant. It's like some number, some function of A and B, right? So it'll be that number times the first vector, 2, -1, plus the other number, 2B plus A over 7, times the second vector, 1, 3. You can verify that the B's will cancel in the first row, and the A's will cancel in the second row. And so, no matter what A and B are, you can write them as a linear combination of these two vectors. And so the span, in other words, if you wanted, the span of these two vectors is all of R2. If you had any vector in R2, here's a recipe for writing that vector as a linear combination of these two vectors, right? Great. Okay, let me give you an awesome example. The standard unit vectors span Rn. If you don't believe me, set up the augmented system that we just did. It'll look like this: 1, 0, 0. Here's the columns. We'd take our standard vectors, write them as columns in a matrix, and then we want to write A, B, C, D, I guess. And I'm doing R4 apparently. A, B, C, D. We want to do we want to write A, B, C, D, any vector in Rn, as a linear combination of the standard unit vectors. Yeah, what you do is you just take A times the first standard unit vector, B times the second one, C times the third, D times the fourth, and so on. You just extract the entries one at a time. That's very nice. So yeah, this is like obvious. It's obvious once you grind your teeth on like a 3x3 example up here. Try one of those, and then you come back and do it with standard unit vectors, and it's like, wait a second. All we do is just like the matrix is already in reduced row echelon form. You just read the answer. Okay, so that's enough about spanning sets for now. I want to talk now about linear dependence, and this is where we're going to camp for pretty much the rest of this video. So, what does it mean for a set of vectors to be linearly dependent? So linear dependence, okay, so we have a set, so suppose we have a set of vectors, v1 all the way up through vk. We call that set linearly dependent if you have scalars, c1 through ck, not all zero, which, so at least one of them is non-zero. And by the way, I know, okay, before I finish the definition, pay attention to that clause. It's one of the stumbling blocks for up and coming linear algebra students to be like, oh wait, I can come up with some scalars. Notice what we're trying to do is, okay, what do we have to do with these scalars? We take c1 times v1, c2 times v2, and so on, all the way up to ck times vk, add them all together and get the zero vector. That's what it means for a set of vectors to be linearly dependent. And you might think, oh, well, let me just take 0 times the first vector, 0 times the second one, and so on, all the way up to 0 times the last one, add them together, and then, great, you got the zero vector. So every set of vectors is linearly dependent. No. You need to have at least one non-zero scalar. Otherwise, what a senseless definition. Okay, great. And by the way, if the set of vectors is not linearly dependent, we call it linearly independent. Okay. Yeah, great. Here's an example, just so that you can see this worked out. I can take these three vectors together are linearly dependent, because if I take 1 times the first one, -2 times the second one, and 0 times the third one, I get the zero vector. Now, remember I said that at least one of these vectors has to be non-zero, or one of these scalars has to be non-zero. It's okay to have some of the scalars be zero. In fact, sometimes you need some of the scalars to be zero. But it's not strictly, like, as long as one of them is non-zero, it's a valid collection of scalars to call the set linearly dependent. So this is linearly dependent. These three, 2, 6, 1, 3, and 4, 1 are linearly dependent. For now, we're going to explore the concept of linear dependence versus linear independence. This is going to feel like a bunch of definitions and theorems about like how to find whether things are linearly dependent or not, and no reason, like why, like who cares about linear dependence. This is a very a really important concept, but you're gonna have to wait for why it's very important. But basically, when you find a linearly dependent set, the problem is over. Or when you find, usually, if you find a linearly dependent set, your problem is usually done. So that's the general feeling for linear dependence. It's like, this is how you end your problems. Let's start with a theorem though. So suppose you have vectors v1 up through vk. those vectors will be linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the other ones. Okay, so remember this is an if and only if proof or statement, and so to prove it, we assume one of the statements and use it to prove the other one. Let's go forwards first, or let's go backwards first. So I'm gonna do this one first because it's easier. Uh, this one's boring, actually. Right? Suppose one of the vectors can be expressed as a linear combination of the other ones. So suppose v1 equals, I'm just going to write c2 v2 plus dot 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 all the way up to ck vk. Suppose that. Now, you might think that I'm cheating because it says at least one of the vectors can be expressed as a linear combination of the other ones. How do we know it's v1? Okay, that's a good question. You should be suspicious of what I'm doing here. What I'm doing is a logical shortcut. We call it without loss of generality. In fact, it's such a nice thing. You will often hear people say "willog," without loss of generality. The idea is the argument that we're about to employ works whether it was v1, v2, vk. In fact, this set is just a collection of vectors. If I have to, I can switch the order around, right? And then relabel them v1 up through vk so that it always is v1 that is the linear combination of the other ones. So yeah, is it cheating to call it v1, to say that v1 is the one that's the linear combination? Yes, we'll just say without loss of generality. Now it's not cheating, right? Without loss of generality, suppose that v1 is the vector which is a linear combination of the other ones. Okay, this is why we wanted to talk about this. Okay, great. And then, okay, well, v1 minus c2 v2 minus all the way up to ck vk. What is this equal to? What is this expression equal to? It better be 0, right? It doesn't even matter what ck vk are. If v1 is equal to this other expression, then subtracting that whole expression across the equals sign will give you 0. No matter what ck and vk are. And the coefficient on v1 is a 1. In particular, it's not 0. So the vectors are linearly dependent, right? This is exactly what it means for vectors to be linearly dependent. You have to have a bunch of scalars, at least one of which is non-zero. Here it is. Such that when you do a linear combination, you get the 0 vector. Such as when you do c1, v1, and all the way up to ck, vk, you get 0. Now, I guess technically the scalars are negative c2 and negative c3 and negative ck and whatever. But those are still scalars. They're real numbers, right? And so thus the vectors are linearly dependent. That's it. Let's go the other way now. So this time we suppose that the vectors are linearly dependent. In other words, suppose c1 v1 plus c2 v2 plus dot 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 plus ck vk is the zero vector. So we suppose this from the start, and now we want to prove that at least one of the vectors can be written as a linear combination of the other ones. Okay, without loss of okay, very importantly, part of the definition of linear dependence is that one of these scalars, C1 up through CK, is non-zero. Suppose, without loss of generality, that C1 is not zero. It could have been that like C1 was equal to zero, but C4 was not, or something. Okay, if you have to, addition commutes, so just rearrange the sum so that the first one is non-zero. Then V1, we can just write it. Okay, just subtract everything over to the other side except for V1, and then divide both sides by C1, so that V1 equals negative C2 over C1 V2 plus, minus, all the way up to minus CK over C1 times VK. Again, we're allowed to do that because C1 is not equal to zero, right? Then we're allowed to divide by it. That's what we needed. And now now we've written V1 as a linear combination of all the other vectors. That's it. Linear combination, right? We need a bunch of scalars times each of those vectors. And yeah, here are your scalars. Negative C2 over C1 all the way up through negative CK over C1. That's it. The proof has a lot more detail and is stated a lot more precisely. This is meant to be to give you basically the main idea. This is correct as well, but it's a little bit looser than the way that the book sets it out. Okay, so we have some examples. First of all, any set of vectors containing the zero vector is dependent. Why? Because if you wanted to create the zero vector out of a set containing the zero vector, just take 1 times whatever. Okay, we'll do like this. 1 times the zero vector plus 0 times V1 plus all the way up through 0 times VK. This is annoying. This is really annoying because what did I do? I did the thing that I told you not to do, which is, just multiply all of the vectors times 0 and then add them together. Yeah, you'll get the zero vector. But I didn't multiply all the vectors by 0, did I? That vector got multiplied by a non-zero scalar. It was the zero vector. Since someone handed me a set of vectors that included the zero vector, I'm free to multiply that one by anything that's not 0 and multiply the other ones by 0. It doesn't matter. This linear combination has a non-zero scalar, namely the number 1. And that was all that we needed. We can have the other ones be 0 as long as we have at least one non-zero scalar, which we do. It's just being applied to the zero vector. But there were no restrictions on what vectors are allowed to be included. We just have to concede that if my set of vectors contains the zero vector, it is just necessarily a dependent set. Okay, great. Another way of thinking about that, by the way, is that by the statement of theorem 2.5, if at least one of the vectors can be expressed as a linear combination of the other ones. Well, any linear combination of the other ones, I can always express, I can express this vector easily as a linear combination of the other vectors. Just do 0 times all of them. And taking a linear combination of all the other vectors is different. We're allowed to use any scalars for that, and it's very easy to use any, like, with no restrictions, use any scalars to create the zero vector in that set. You just that one we're allowed to take 0 times all of the vectors in the set. So it is okay. Admittedly, it seems like I'm cheating or I'm bending the rules, but I encourage you to go back and verify that I haven't broken any rules. Yeah. Okay, great. Or you should challenge me during office hours on this point, because it's one of those things where it's really fun to debate, and you can because everything is perfectly well defined and consistent. It's also impossible to lose that debate. So yeah, okay, great. Um, let's try something that's less obvious. So determine whether this set is dependent. Okay. In other words, we have to go and figure out if so. How do we determine whether a set is dependent? We have to say, can we write C1 times 110 plus C2 times 101 plus C3 times 011? Can we find scalars C1, C2, and C3 not all equal to 0 such that 0, 0, 0 is contained inside of is a linear combination, or such that 0, 0, 0 is the thing that you get when you take a linear combination for those scalars. That's a system of linear equations, right? Just like before. In fact, this is a homogeneous system of linear equations. Homogeneous because the constant terms of the linear system are all 0. Let me write down the actual system. It's C1 plus C2 equals 0. C1 plus C3 equals 0. And C2 plus C3 equals 0. Homogeneous system. I will tell you, okay, let me do this. We'll put this guy underneath, and then I'll write its augmented matrix. It's 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. When you row reduce this guy, it's not so bad. You just add the rows together. I guess subtract a little bit. When you put it in reduced row echelon form, the augmented system is this: 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. In other words, there is a unique solution to this system of linear equations where C1, C2, and C3 are all precisely 0. C1 equals 0, C2 equals 0, C3 equals 0. That's a solution to the system of linear equations. In fact, it is the unique solution to the system of linear equations, right? Because there are no free variables. And C1, C2, C3 are all 0, which means this system is linear, or these three vectors form a linearly independent set. You cannot okay, let me say it less directly. The system, it does not form a dependent set, right? Because to form a dependent set, you have to find 3 scalars, C1, C2, C3, which are not all 0, that can be used to make the 0 vector. Well, that's impossible because this is the only solution to that system of linear equations. So is it dependent? No. Let's try another one. So we'll do the same thing. we have a system of linear equations that corresponds to this. So we have, right, we'll do, I probably won't show as many steps. We'll just do C1 plus C2 plus C3 equals 0. 2C1 plus C2 plus 4C3 equals 0. And 0C1 minus C2 plus 2C3 equals 0. This system. It's not that bad. Let's write the augmented matrix and actually row reduce it. It's not so bad. 1 1 1 0 2 1 4 0 0 minus 1 2 0. We already have a leading one here. Pivot around it, and we have so take row 2 minus 2 row 1. That will clear out that entire column. We'll still have 1 1 1 0 on top. But then when we take 2 copies of row 1 away from row 2, we have a 0, then a minus 1, a 2, and a 0. And then the bottom row will be 0, minus 1, 2, 0. Wait a second. If I just subtract row 2, so subtract row 2 from row 3, so row 3 minus row 2. Notice that bottom row is gone. I'm also going to, while we're at it, negative row 2. That way, we have this is a minus 1. In reduced row echelon form, we're going to need that as a positive 1. So the top row will still be 1, 1, 1, 0. The second row will be 0, 1, minus 2, 0. And the bottom row will be all zeros. I guess if you want to negate it first and then add it to the bottom row, it doesn't matter. 0, 0, 0, 0. And the last step is to subtract row 2 from row 1. So 1, 0, 0, 0, 1, 0, 3, minus 2, 0, 0, 0, 0. So in other words, C1 plus C3 equals 0. C2 minus C3 equals 0. Sorry. C1, what? C1 plus 3C3 and C1 minus 2C3, right? These guys, those numbers, equals 0. But, oh, and of course C3, oh, we have no condition. So the bottom row says 0 equals 0. So this is all there is to it. C3 is a free variable. But, so I'll just put C3. Well, let's write these as, let me rewrite these equations so that we're solving for C1 and C2 in terms of C3. That'll be a little bit easier to look at. So C1 equals negative C3, negative 3C3. And C2 equals positive 2C3. And C3 is literally C3. When we do this, that's true for, since C3 is a variable, is a free variable, we can plug in any number for it to obtain a valid linear combination of these 3 original vectors, which gets us the 0 vector, which solves the system of linear equations. Let's try one. Let's try C3 equals 1. So when we do that, C1 equals negative 3, C2 equals 2, C3 equals 1. In other words, negative 3 times the first one, 1, 2, 0, plus 2 times the second one, 1, 1 minus 1, plus 1 times the third one, 1, 4, 2. Obviously, by the way, if C3 equals 0, you get a valid linear combination. But if you put C3 equal to 0, then all three scalars are precisely 0. And so that linear combination, like that is a solution to the system. However, it doesn't prove linear dependence, right? We need at least one non-zero scalar. So here I've produced actually three non-zero scalars. Do they work? Let's try it. Negative 3 plus 2 plus 1, that's 0. Negative 6 plus 2 plus 4, that's 0. 0 minus 2 plus 2, that's 0. So there we have it. This is, yes, they are linearly dependent. Good. Okay, let's distill that process into a theorem. So let A be the n by m matrix v1 all the way through vm, where the vectors v1 through vm are column vectors in Rn. Let's just do a sanity check real quick. N by m matrix means it has n rows and m columns. The m columns, there's one for each of these vectors, so that's good. Right, m, whatever, yeah. Okay, and then the rows, well, they're column vectors, which means each one of them has column vectors in Rn, so each one of them has n entries. So when you stack them vertically, you've got n numbers stacked vertically in each column, which means you've got n rows in this matrix. So it's an n by m matrix. Okay, then the columns v1 through vm are linearly dependent if and only if the homogeneous linear system with whose augmented matrix is like A augmented with 0, right? If and only if that augmented matrix or that linear system has a non-trivial solution. Non-trivial. Remember that we saw last time that for a homogeneous system, there will always be at least, like that system is always consistent. There's always at least one solution, namely the zero vector, or the one where you take all zeros. But we call that the trivial solution. So we want another solution. Let's try it. So let's see if we can prove this. This is going to be just using, this proof will go just by using theorem 2.4. Okay. Again, it's an if and only if statement. So we assume that the column vectors are linearly dependent. That means we can write them as a linear combination with a non-zero scalar to get to the zero vector, right? The solution then, okay. Remember theorem 2.4? It just tells us, well, I'll just read it to you. I'll just go back up and look at it. Theorem 2.4 tells us that the system is consistent if and only if the vector that's forming the augment is a linear combination of the columns of the matrix A. Well, in other words, here in our linear system, we're told that the zero vector is a linear combination of those other vectors. But because we're assuming that the vectors v1 through vk are linearly dependent, that means that there's a non-zero linear combination. So there's a non-zero linear combination of V1 all the way up through Vm, which produces the zero vector. Producing like, 0. That is what is given by theorem 2.4. But that means those scalars are a non-trivial, like by definition, those scalars are a non-trivial solution to the augmented system. Yeah. But if you read this argument backwards, if you have a solution uh, to a non-trivial solution to this system, then there is just by the statement of theorem 2.4, there is a non-trivial linear combination of the columns of A producing the zero vector. Then by definition, those vectors are linearly dependent, right? So you just have to do a little bit of mind twisting, but the amount of things that we have to say is very small for this proof. It's a very interesting proof. But I don't want to get bogged down in the proof of this theorem. I want to just reference its utility. In other words, to check whether a bunch of column vectors are linearly dependent or not, set up a homogeneous system and then ask if it has a non-trivial solution. That's all there is to it, right? Okay, let's do that twice. Well, we'll do that once, actually. Once more. We already did it twice. One more time. The standard unit vectors are linearly independent. Let's set up the following homogeneous system. 1, 0. I'll do it with R4 again. This is precisely the homogeneous linear system called for by theorem 2.5. And now we ask, does it have a non-trivial solution? And the answer is, of course not, which means the column vectors are not linearly dependent, so they must be linearly independent. It's pretty nice. We don't have to do any work for this one. Instead, suppose we have row vectors. So you can do this, right? You'll recognize these row vectors as the vectors from that we did as one of our first examples. They were written in that example as column vectors. So I want to present to you another way of checking whether vectors are linearly dependent. This is really fun because we just write them as rows in a matrix this time. So let me just write down a matrix which has these row vectors as its rows. 1, 2, 0, 1, 1, minus 1, 1, 4, 2. No augmented matrix, no coefficients, nothing like that. Just straight up write it as a row, write each row vector as a row in a matrix. And then row reduce this matrix. When you do, okay, let's just do that real quick because I don't want to spoil it. So we're going to subtract row 1 from the other two. So row 2 minus row 1 and row 3 minus row 1. This will give us 1, 2, 0, 0, minus 1, minus 1, 0, 2, 2. And then, just one more step, take row 2 minus row 3. So row 3 minus, or plus 2 row 2. So we're going to just row echelon form, not reduced row echelon form. The top row doesn't change, obviously. The middle row does not change, and the bottom row becomes a row of all zeros. Now the fact that it's okay, so notice that what we did was we did first to get this bottom row. So let's just reverse engineer what we did to get the bottom row. So we have that the 0 vector is the bottom row, row 3. Which was, okay, it was like row 3. So it's row 3 of this matrix, right? This matrix. But that row was created by taking, how did we create that row? We took this row 3. So I'll just write it. I'm going to abuse notation here. But it's this row 3. Okay. Plus 2 times this row 2. But in terms of the original guys, so how did we get each of these two rows? Well, this row 3, the middle row 3, I guess. I don't know. Well, anyway, that guy was the original row 1. Sorry, was the original row 3 minus the original row 1. And this middle row 2 was the original middle row 2 minus the original row 1. Okay, in other words, so we started at the very beginning with row 1, row 2, row 3, right? We took, we just did these two row operations, row 2 minus row 1 and row 3 minus row 1 to produce two new rows, which we then added one of them to the other one to get a row of all zeros. Notice I kept the 2, so we're gonna have to distribute. But okay, when we do this, let me just distribute out and then recombine like terms. So we'll have row 3, and these are like original rows. Row 3 minus row 1. Okay. Plus row 2 to row 2. Minus row 1 minus another 2 row 1s. So minus 3 row 1s. So apparently the 0 vector is row 3, which is 1, 4, 2. The original row 3, which was given to us as a set of 3 row vectors. Okay, plus 2 times row 2, the original row 2. So 1, 1, minus 1. Minus 3 times the original row 1. 1 minus 2, 0. And if you check, this is exactly the linear combination that we had before. This is a lot of work, but the point is, by doing elementary row operations to a bunch of row vectors that were handed to you originally, if at the very end of the process you ended up with a row of all zeros, then you just have to backtrack through what you did. You did a bunch of linear combinations of the previous rows, which if you combine them all together, you end up with precisely a recipe for a non-zero linear combination of the original rows which will produce for you the zero vectors, right? The condition is, did you get a row of all zeros when you were doing your row reduction? Okay, linearly dependent is the conclusion. Okay, this is, again, this is like a third way of checking whether or not a set of vectors, this time row vectors, are linearly dependent or not. Let's state it as a theorem though, because the theorem is not the obvious statement. So it says let A be the m by n matrix whose rows are the row vectors v1 through vm, which are row vectors in Rn. Let's just make sure that makes sense. M by n matrix means it has m rows and n columns. Each row is a row vector with n entries, right? Because it's a vector in Rn. So yes, A is that matrix. Okay, then v1 through vm are linearly dependent if and only if the rank of A is less than m. Okay, remember the rank of A. What is that? That is the number of non-zero rows in the row echelon form of that matrix, in a row echelon form of that matrix. If you bring that matrix into row echelon form, you'll get some number of rows of zeros, and then the rest will be non-zero rows. If the number, okay, and now if the number of non-zero rows is strictly less than the number of original rows, then the system is linearly dependent. Okay, well, anyway, proof. The proof is an observation. Elementary row operations on the rows of A can be decomposed as linear combinations of V1 through Vm. So this is observation number 1. Observation number 2, the rank of A is less than m if and only if the row echelon form, yeah, which is obtained by taking linear combinations of the rows of A, row echelon form of A, contains a zero row. So, put those things together, then, in this case, there is a non-trivial linear combination of the row vectors v1 through vm. v1 through vm, yielding the zero vector. That's it. We just notice these three facts. Okay. We're going to end with one last theorem, theorem 2.8, which is really nice. It will help you tremendously, at least on one step of the written homework, which is, but also just in life. Like this is always the first test that I apply when someone asks me, "Oh, is this set of vectors linearly dependent?" The very first thing I do is count the number of vectors, because any set of m vectors in Rn is linearly dependent if m is greater than n. In other words, four vectors in R3, any four vectors in R3 are dependent. Why? Let's use theorem 2.6. That's the one with column vectors. We could also have done 2.7 with row vectors, but I prefer column vectors. So let V1, Vm be column vectors. In Rn, of course. And let A be this matrix, V1 all the way up to Vm. So we're just doing the setup for theorem 2.6. By theorem 2.6, the result from theorem 2.8, these vectors are linearly dependent. We'll say V1 to Vm are linearly dependent if and only if this augmented matrix, the linear system corresponding to this augmented matrix, has a non-trivial solution. But we had a theorem it's theorem 2.3, so I guess that was probably in the previous section, which said that this has to happen. This must happen. It's the rank theorem, actually. By the rank theorem, the number of free variables is going to be the rank, the number of leading terms minus the rank, or is minus the rank. Yeah. It's the number of rows minus the rank. This must happen. Number of columns minus the rank. Okay. This must happen by theorem 2.3. Too many columns. So we have at least one free variable. Since we have a free variable, we're free to plug in a non-zero number for that variable to obtain the desired linear combination. This is like more work. This is like a lot of work to just distill an observation. So we're just going to say this is the end of the proof. This is very short observation. Good. Okay, and that's. I'm also not going to give an example. You want an example? I actually gave an example. Here you go. Any four vectors in R3 are dependent. There's an example. And that's it for this video as well. That's the end of section 2.3. So next week we'll finish up chapter 2 and get started in chapter 3. I will see you in the next video.